Good day and welcome to this Chem 16 lecture on chemical bonding. On this first slide, we see the expectations from the course. Please take a moment to read them. All right, crucial in this regard is a discussion on Lewis theory. At the end of the section, what we hope is that you develop the criteria in order to decide how elements bond to each other, in what manners, and how the bonding will allow you to be able to predict or rationalize observations that you see in the laboratory. There are several references which you can use for this topic. A major reference for this course is Chemistry, the Molecular Nature of Matter and Change by Silberberg. Also very useful is General Chemistry, Principles and Modern Applications by Petrucci et al. However, if you would like to turn to online resources, I recommend looking at these videos produced by the Khan Academy. There are videos which pretty much cover the topics also discussed in this lecture. In the previous section of Chem 16, you learned how the periodic table of elements was arranged. For instance, you know that going down this row of the periodic table, the elements in a row would all have the same valence electron configuration. So for instance, if you look down this first row, you would know that their valence electron configurations would be S1. Whereas here in this next row, you know that the valence electron configurations would be S2. And then looking now at this side of the periodic table, you know, for instance, that on the extreme right, going down this row, you know that the elements would have the valence electron configuration of S2p6. And the reason why it is called the periodic table of elements is that as you add electrons to the orbitals of an element, according to the Aufbaubilder principle, you then start arranging your elements in such a way that because they precisely have the same valence electron configuration, they also exhibit the same chemical properties. So for instance, here highlighted in this circle is the metal sodium. Sodium is a metal, and as a metal, it will tend to form cations, meaning that it tends to lose electrons. And we expect the same metallic sort of behavior also from lithium, from potassium, from rubidium, from cesium, and so on. Whereas if we look at the other side of the periodic table over here, for instance, let's take oxygen, which is encircled in red. Oxygen is a nonmetal, and as a nonmetal, it would form anions, or it would take up electrons and would therefore become negatively charged. However, when we look at the extreme right of the periodic table, these elements down this row we know are referred to as the noble gases. And what is characteristic about them is that they have an electron configuration, as we said earlier, of S2p6. It's described as a stable configuration, and that stability is termed as well, being attributed to the octet rule. Why octet? Because, well, we have 2 electrons in the s orbital and 6 electrons in the p orbital. 2 plus 6 equals 8. And this is also referred to as the noble gas configuration. And what is characteristic about the noble gases is that they are actually, by and large, chemically inert. And the reason for this is that since the s orbitals and p orbitals are completely filled with electrons, it is very difficult for them to engage in electron donation, electron gain, or electron sharing. And hence, they are stable. And this is an important clue with respect to predicting the chemical reactivity of the elements, because what we will see later on is that the tendency is to form the noble gas configuration in order for a compound to be stable. There are several types of chemical bonds which we will cover in this lecture. They are listed here on the slide. There's the ionic bond, the covalent bond, and the metallic bond. Ionic bonds are formed between metals reacting with nonmetals, and the nature of the interaction is electron transfer or donation. Specifically, that the metal will lose an electron, forming a cation, and that electron will then transfer to the nonmetal, which then becomes negatively charged and therefore forms an anion. A common example over here is the reaction of sodium with chlorine. Sodium is a metal, chlorine is a nonmetal. When these react, sodium donates an electron to chlorine, forming the salt sodium chloride. Now, covalent bonds are formed between nonmetals reacting with nonmetals, and the nature of the interaction between nonmetals with nonmetals is electron sharing, and the resulting product is a covalent compound. So a common example is, for instance, hydrogen, which is a nonmetal reacting with another hydrogen to form hydrogen gas. The principles of how these bonds are formed, we will go over in the lecture. And finally, there is the metallic bond. Well, there is no reaction per se of which we can speak about. Simply that in a metal, what the model which describes the interaction between metal atoms is that what you have actually is a group of metal cations which are in a sea of electrons. And for this reason, because there is this sea of electrons, we find that metals make very good electrical conductors. And there are many of these, as you see in the periodic table: sodium, magnesium, iron, zinc, and so forth. As I said at the start of this lecture, crucial in this topic is understanding how to use Lewis theory in order to be able to understand chemical properties and reactivity of the elements. So let's begin with discussing electron Lewis dot symbols. For main group elements, the way Lewis represented elements was using a letter, which is, well, the symbol for the element, but which also represents the inner core electrons of that element. And then this letter is then surrounded by dots, which represent the valence electrons of the element. So for instance, let's take this element, nitrogen. The valence electron configuration of nitrogen is helium 2s2 2p3. So how many valence electrons are there? Well, 2 plus 3 equals 5. There are 5 valence electrons, 2 of which are paired and 3 are unpaired. How else do we know this? Well, when we look at the position of nitrogen in the periodic table, we see that it is situated in group 5a, and therefore we can immediately say that nitrogen has 5 valence electrons. Let's take a look now at these elements from period 3. Over here we have sodium, which is in group 1a. The valence electron configuration of sodium is neon 3s1. So since there is since sodium has 1 valence electron, then we therefore represent this with a single dot beside sodium. What about for magnesium? Magnesium, which is in group 2a but still in period 3, has a valence electron configuration of neon 3s2. Therefore, 2 valence electrons, 2 dots. And then going to the right of the period, here we have chlorine. The valence electron configuration of chlorine is neon 3s2 3p5. 2 plus 5, there should be 7 dots around the symbol for chlorine, and we have 1, 2, 3, 4, 5, 6, 7 dots. Okay, we can now use these Lewis electron dot symbols in order for us to represent compounds using or drawing them using Lewis structures. So what is a Lewis structure? Lewis structure is a combination of Lewis symbols to depict either electron transfer or electron sharing between atoms in a chemical bond. And it's important that the dots or the electrons in the Lewis structure are paired in such a way that the octet rule is satisfied. Okay? So let's take this first example of metal with nonmetal, the formation of the ionic bond. So lithium is a metal and fluorine is a nonmetal. As we said previously, since lithium is a metal, we know that in order for it to, it has a tendency to lose electrons. And why does it have a tendency to lose electrons? Because looking at the valence electron configuration of lithium, helium-2s1, if lithium were to lose that one electron, it would achieve the noble gas configuration of helium gas. Whereas when we look at fluorine, it being a nonmetal, and knowing that therefore it would tend to receive electrons, if it does gain an electron, if we look at its valence electron configuration of helium-2s2 to p5, well, if an additional electron is added to the p orbital, then it achieves also a noble gas configuration of 2 plus 6 equals 8. So how do we represent this using Lewis structures? So here we have the Lewis electron dot symbol for helium, and here we have the Lewis electron dot symbol for fluorine. This one electron transfers to this fluorine, therefore lithium becomes cationic and fluoride becomes anionic, and the resulting valence electron configurations of the corresponding ions are lithium plus is now 1s2 or helium, whereas fluoride is now helium 2s2 2p6 or neon, and hence noble gas configuration has been achieved for the two elements in the ionic compound, and therefore it is stable. Let's look at this example. How would we combine aluminum with oxygen? The valence electron configuration of aluminum is neon 3s2 3p1, whereas the valence electron configuration of oxygen is helium 2s2 2p4. How do we combine aluminum and oxygen in such a way that the octet rule is satisfied for all the elements involved? So we know that aluminum has 3 valence electrons and that oxygen has 6 based on their valence electron configurations. Well, we stop and think about it a bit, and we realize that actually for all parties to be satisfied, we will need 2 aluminums, each of which having 3 valence electrons, need to combine with 3 oxygens in order for the octet rule to be satisfied for everyone. Therefore, the resulting Lewis structure for the ionic compound is 2 aluminum 3 plus with 3 oxide 2 minus. Why is this important? It's important because Lewis theory allows us to predict the stoichiometry of the final compound. There are many examples which you can find in the textbook for further practice, or you can find also online. So please look them up at your own initiative. As a result, of the way metals bond with nonmetals to form ionic compounds, there are some interesting properties which can be observed in the lab. Let's look first at water. Water, we know, is not an ionic compound. It's a very common solvent. And what our daily experience shows is that the melting point of water is at 0 degrees Celsius, while its boiling point is at 100 degrees Celsius. When you compare the melting points and boiling points of water with these ionic compounds, lithium fluoride, sodium chloride, and potassium bromide, we see that the melting points are way, way, way much higher, and even more so the boiling points. Why is this so? This is so because the nature of the interaction between cations and anions is electrostatic. And electrostatic forces, as we know from physics, is a very strong form of interaction. And hence, in order for an ionic compound to melt, which will therefore mean that the ions will then have to start moving around, well, you're going to need a lot of energy. And hence, this is reflected in the very high melting points, even more so with the boiling points, because this means separating species. What other properties do we observe in ionic compounds? Well, they exhibit very good electrical conductivity in solution and in molten form. In solution, because then the ions separate in the solvent such as water, and therefore we can get ions moving around, and then same thing as well in a molten salt. And then also ionic solids in the crystalline form, well, they tend to crack. And they crack because when we look at the solid lattice of an ionic compound, well, what we see are alternating charges of positive and negative, or cations and anions. And if a force is applied to the solid lattice, well then, if the force is strong enough, it may force the like charges to come face to face with each other, which therefore repel, and hence the solid cracks. All right, let's consider now how nonmetals interact with each other, nonmetal with nonmetal, and therefore forming a covalent bond. So as mentioned previously, nonmetals react with another nonmetal by electron sharing between the nonmetals. So for instance, let's look at this hydrogen and this hydrogen. Both of them have a valence electron configuration of 1s1. But if two hydrogen atoms were to interact, we see that if this electron interacts with this, then you get an electron configuration of s2, which is stable or fully filled. And hence we can represent it this way, that each of the hydrogen atoms shares an electron, and therefore what results is a bond pair. And this bond pair can also be represented by a single line, which is why we can also refer to it as a single bond. What about for oxygen? Oxygen, we know, has 6 valence electrons. So here we have 1, 2, 3, 4, 5, 6 around this oxygen, and another 1, 2, 3, 4, 5, 6 around this oxygen. The valence electron configurations of oxygen is 2s2, 2p4. So how many electrons does each oxygen need to share with the other in order to be able to satisfy the octet rule? The answer is 2. And as a result, there are 2 bond pairs which are formed, or otherwise also called a double bond. Now let's look at the example of nitrogen. Nitrogen has a valence electron configuration of 2s2, 2p3. And if nitrogen were to react with another nitrogen, in order to satisfy the octet rule, then each nitrogen will have to share 3 of its electrons with the neighboring nitrogen. Therefore, 3 bond pairs are formed, and resulting in a triple bond. The number of bonds connecting atoms together is referred to as the bond order. And the higher the bond order, the higher the resulting bond strength, and also there's a corresponding decrease in the bond length, the reasons for which we will discuss in the next video. For now, what I would like us to think about are some of these questions to test our ideas. For instance, number 1, can nitrogen and nitrogen form only a single bond? Why or why not? And the answer to this question will lie in an understanding of the octet rule. Next question. If carbon combines with hydrogen using only single bonds, what is the resulting compound? As I mentioned earlier, Lewis' theory allows us to predict the stoichiometry of compounds based on the number of valence electrons of each element which are available for bonding. So that concludes the first video for this topic. We've already discussed the different types of chemical bonding, differentiated ionic and covalent bonding, and looked at Lewis structures of ionic and covalent compounds. In the next video, we will see how differences in electronegativity allow us to predict some chemical and physical properties of resulting compounds. And please move to the next video.